Welcome, everyone, to Georgetown University's Gaston Hall. Our program will begin in a moment. Please take a second and silence your phones. Thank you. Please welcome to the stage John J. DeGioia, President of Georgetown University, and Dr. Anthony Fauci, Distinguished University Professor.
This is beautiful. Well, good afternoon, everyone, and welcome. I want to thank you all for being here for this special event in the life of our university community. This afternoon, we're honored to have with us for this year's Whittington Lecture, Dr. Anthony Fauci, who joined our community this past summer as a distinguished university professor in the School of Medicine and in the McCourt School of Public Policy. And it's a privilege to have this opportunity to engage in conversation and reflection on this issue of importance to our global community, pandemic preparedness and response, lessons from COVID-19. For more than 2 decades, the Whittington Lecture has honored Dr. Leslie Whittington's memory. Dr. Whittington was a beloved member of our faculty, and she and her husband Charles, their 2 young daughters, Zoe and Dana, were killed on September 11th, 2001, when American Airlines Flight 77 was hijacked and crashed into the Pentagon. Her passing was an extraordinary loss for our community, and it continues to be deeply felt. In her scholarship, her teaching, her service She enriched the lives of so many members of our community, embodied the very best of our work as a university. She advanced groundbreaking research on the intersection of tax policies and family decisions, helped to build our Georgetown Public Policy Institute, now our McCourt School of Public Policy, and she mentored and supported countless students and colleagues in their work. We remember her and what she meant to this community in this lecture series. And across the years, the Whittington Lecture has focused on a range of topics, from the impact of climate change to fighting poverty, with reflections from leaders who each share a deep commitment to service and to the common good. This afternoon, we have the privilege of hearing from Dr. Fauci, a dedicated public servant, a visionary global health leader. His extraordinary career is a model of a life lived in service to others, to our nation, to our world. Over more than half a century at the National Institutes of Health, he led the development of drugs and vaccines, advocated for preparedness against infectious diseases, helped to lead the fight against HIV/AIDS nationally and globally, and guided our national response to the COVID-19 pandemic. He has served in 7 presidential administrations, helping to protect the health of millions of people during a range of public health challenges over that half century. And he's made important contributions to our understanding of immunology, infectious diseases, and public health. We're deeply grateful to have him as a member of our Georgetown community, and this afternoon to engage his reflections on pandemic preparedness and the lessons our global community can learn following the COVID-19 pandemic. So thank you, Dr. Fauci, for your presence here this afternoon. I know we're all looking forward to your reflections. And I would now like to welcome Anirudh Srivatsan, the McCourt School's 2024 Whittington Scholar, to the podium to introduce Dr. Fauci. Thank you.
Wow, this is a lot of people. Good evening, everyone, and welcome to this year's Whittington Lecture. My name is Anirudh, and I'm a second-year graduate student pursuing a Master of Public Policy here at the McCourt School. Before I introduce our distinguished speaker for this evening, I would like to take a moment to celebrate the fact that today marks the first day of Black History Month. While February should not be the only day or month that we honor the legacy and contributions of African Americans across the US, this month does serve as an important reminder to all of us that the rights and freedoms that we do enjoy today are not a given. As we sit here comfortably in this hall today, safe and secure, there are many groups across the world that continue to struggle and fight against their oppressors. So I would like to ask that all of us here continue to learn about, advocate, and fight for the things and causes we believe in. Because we know that none of us are truly free until all of us are free. With that, it is an honor to stand here before you today to introduce a figure who has not only left an everlasting mark on public policy, but has also been a guiding force in shaping policies that have transformed lives globally. Tonight, we have the privilege of delving into the wealth of experience of a true luminary, Dr. Anthony Fauci. For over 5 decades, Dr. Fauci has been at the forefront of the fight against infectious diseases, serving as the director of the National Institute of Allergy and Infectious Diseases, the NIAID, for an astounding 38 years. His tenure at the NIAID has been a testament to his unwavering dedication, marked by groundbreaking research on a spectrum of diseases from HIV/AIDS to malaria and Ebola, showcasing his commitment to addressing both established and emerging threats. What sets Dr. Fauci apart is not just his scientific acumen, but his pivotal role in crafting policies that has had a profound impact on public health. As a trusted advisor of 7 presidents, he has played a crucial role in the launch of the President's Emergency Plan for AIDS Relief, a program that has not only saved lives, but fundamentally changed the landscape of global health in the developing world. Amid the challenges of our time, particularly the unprecedented trials posed by the COVID-19 pandemic, Dr. Fauci has emerged as a beacon of reason and resilience. Serving as the White House's chief medical advisor, he navigated the turbulent waters of a pandemic with grace, advocating for science-based guidance and public health measures in the face of political pressures. His calm demeanor, clarity in communication, and steadfast commitment to truth have become a source of inspiration during a period of immense uncertainty. Tonight, we are privileged to hear directly from Dr. Fauci, drawing from his vast experience to reflect on the lessons learned from COVID-19 and offering his insights into the future of public health. Join me in extending a warm welcome to welcome a true public health leader, Dr. Anthony Fauci.
Okay. Thank you so much for that very kind introduction, Anirudh, and thank you so much, Dr. DeGioia, for welcoming me here. I want to start off by first expressing how pleased and honored I am to be now a member of the Georgetown family. As Jack mentioned, I have a joint appointment in the School of Medicine and in the McCourt School of Public Policy. So I've been sort of a Hoya for the last 40 years, since my wife, Christine, is a double Hoya, having graduated from the college and then getting her PhD here years ago. So I'm very pleased to join this family. As you could see on this first slide, I'm also very pleased and humbled, actually, to have the opportunity to pay homage to Leslie Whittington and her family. As Jack mentioned, the terrible tragedy of Leslie and her husband, Charles Falkenberg, and their two children who died tragically on September the 11th of 2001 when American Airlines Flight 77 was hijacked and crashed into the Pentagon. Leslie helped build the Georgetown Public Policy Institute, which is now the McCourt School of Public Policy, and served as the Associate Dean from 1999 through 2001, and she was a beloved, committed, and effective teacher in economics, public finance, and other areas. So let's now start off with this discussion of SARS-CoV-2, COVID, and the lessons learned. Just very, very quick few slide introduction. I don't want to get too technical on it, but it's important to understand a little bit about this most insidious virus before we talk about lessons learned. It's an RNA virus. It's a large genome. There are multiple subgroups. We refer to them as genera, alpha, beta, delta, gamma. They'll become important in a few minutes when I talk about the different variants that we have experienced over the last 4 years. There's a wide host range. The bat is a reservoir. The wide host range is critical understanding not only the origin of COVID, but the potential origin of future outbreaks. And historically, this causes, as we all know, tragically, severe respiratory illnesses in humans, GI illnesses in certain animals. This is a phylogenetic tree. For those who are not familiar with these, please don't get intimidated by it. It shows the different branches of coronaviruses. And the reason I show it is that I want to point out the similarity between one group and another group of coronaviruses. It wasn't fully appreciated until we got into the original SARS, which I'll mention in a moment, and SARS-CoV-2, which has afflicted us for the past 4 years, is that there were 4 endemic human coronaviruses that cause every year 15 to 30% of all the common colds. And we get reinfected with these coronaviruses, which is a hint about why and how you can get infected with COVID and still get reinfected, because the immunity doesn't last very long. So the 4 yellow highlighted boxes are the 4 common coronaviruses. But then something happened historically that took the coronaviruses from relatively benign sniffles, common cold, into the epidemic arena. And those were two events that occurred, one in 2002, 2003, when we got the first glimpse of severe acute respiratory syndrome that originated in the Guangdong province of China. Interesting comparative with what we went through over the last 4 years. And then in 2012, another coronavirus, the Middle East respiratory syndrome. Of note, both of these came from a bat reservoir, clearly documented, into an intermediate host. With the original SARS, it was a civet cat, which was sold at a wet market in China that led to the infection of humans, which then spread throughout the world. And the Middle East respiratory syndrome, again, a bat reservoir into a camel, into individuals mostly in Saudi Arabia. So SARS-CoV-1 and MERS cause severe human disease. Notice the two yellow boxes which indicate where on that circle of phylogenetic tree of the coronaviruses, somewhat similar to the others. The SARS-CoV-2, what we're dealing with now, today, again, shown on the yellow box, is very close and sequestered with those other viruses. I know it's difficult to see because the print is small, but right next to that are a group of bat coronaviruses, which we feel very likely was the original source of what we're dealing with now. So that's a bit of a background. We all know that in January of 2020, a group of pneumonias was reported from the Central District of China in the city of Wuhan, probably first recognized in mid-December, but brought to the attention of the global health community in the first week of January of 2020. Fast forward a few weeks, and the first travel-related case of SARS-CoV-2 was detected in the United States. And then fast forward 2.5 months, and in March 2020, after we had over 118,000 cases in more than 100 countries with close to 5,000 deaths, the WHO finally declared COVID-19 a pandemic. So now let's really fast forward to today. The global COVID-19 pandemic, as of the last data accumulated a day or two ago, were about 774 million cases, likely a gross underestimate because of the tracking systems we have. The reported deaths are more than 7 million, but when you look at excess mortality, which means not only deaths directly caused by SARS-CoV-2, but related deaths, lack of health care leading to someone who dies of another disease because the hospitals were completely overrun with COVID cases. That goes into the count of excess mortality. And when you add all that up, the excess mortality is felt to be about 20 million people worldwide. Switching to the United States, in a tragic way, and it's really very unfortunate, and that's going to be looking at some of the lessons we'll discuss in a moment or two. The reported hospitalizations were close to 6 million, close to 7 million, but the reported deaths in the United States is 1.17 million, which on a per capita basis is more than almost every single country with one or two exceptions in the world. So given our really good healthcare system, as it were, and all the other good things about our society, we did worse than almost every other country, including low and middle income countries. Now, where are we with COVID today? We don't track it by cases, because how many of us, certainly me, and a lot of people I know, have gotten infected, gotten a test and didn't report the test to anybody? Raise your hand. Everybody? Yeah, okay. So we don't determine by number of tests that are positive, but a really neat way of determining the prevalence is by examining the wastewater, because in the excreta, you get fragments of virus and whole viruses that are excreted, get into the sewage system, and you could monitor, as shown on this slide, the very dark shaded areas are those that have the highest wastewater concentration. The lowest ones, the low shaded, are ones that are the lowest, and the white blanks are those that just don't report wastewater. Okay, now, modeling the economic toll of COVID, it's estimated that it has cost the United States total, lost work, other aspects of the economy, $14 trillion from January 2000 to December 2023. So with that as a core background, let's talk about some of the lessons we learned. I wrote this in an article in the Journal of Infectious Diseases in April of 2023. And there were several important lessons. There were probably 100 lessons. I picked out 10 that I thought were really quite relevant, that were important for audiences to appreciate and understand. So what I'd like to do for the remainder of the time is to go through these 10 lessons and then come to some conclusions. The first lesson when you're dealing with an outbreak like this is to expect the unexpected, because so many aspects of SARS-CoV-2, from virology to transmission, natural history, pathogenesis, epidemiology, were not initially appreciated. We were dealing with a moving target, truly a moving target. So what do I mean by that? First of all, we were dealing with highly mutable viruses which evaded immunity as you had different variants. Now, the next slide I'm going to show, don't get taken aback by it. It's another phylogenetic tree, but it's really very telling. So let's march through it. If you go to the upper left part of the slide, that's January of 2020. And those were the first viruses we called the ancestral strains. And then over a period of several months to a year and a half, we had different variants: alpha, beta, gamma, delta. Remember delta in the summer of 2021 when the president said, hopefully, that we could be independent of COVID as we reached the 4th of July? And then Delta came on the 4th of July, and so much for independence. But then what happened in Thanksgiving, I know because it interrupted my Thanksgiving meal when I got a call from South Africa, that a new virus that was really different. So the length of the line from the original cluster on the upper left of the slide is the phylogenetic distance from the original viruses, which means that when Omicron came, it was very, very different. Bad news for us, for those of us who got infected and those of us who got vaccinated, because the protection against Omicron was significantly less and not overlapping very much with all of the other viruses. I can't express strongly enough how different that is from any other respiratory virus that we've ever experienced, where within one season, albeit a 4-year season, we've had multiple variants of the same virus. That is truly unprecedented. You go to the lower right-hand part of the slide, and for those of us who are getting infected now, last week, last month, you very likely got infected with JN1, which is now more than 90% of the isolates. Far different from those who got infected in January, February, and March of 2000. Now, this slide shows the peaks associated with each of those variants regarding hospitalizations. So you see it says alpha, big peak. Alpha goes away, hospitalizations go down. Delta comes, big peak. Delta goes down, hospitalizations goes down. Look at the hospitalization with Omicron, way, way up. And then all variants of Omicron have had less hospitalizations. The same holds true with deaths in the United States. The same association, different new variant, different spike in both hospitalizations and deaths. Why is that if this is the same virus? And it is. It's a coronavirus. I showed it to you on the phylogenetic tree. And the reason is each of the successive variances, just like a stepwise ladder or a stairway, has increasing growth capacity and increasing ability to evade the immunity that you developed from the prior infection. Mostly evading protection against infection, less so evading protection against severe disease. So what does that mean? That means if you got infected, you could probably get reinfected, but it is unlikely that you will get severe disease after a prior infection and certainly after vaccination. So what does that mean? Do we have to run around chasing all the variants? That would be playing whack-a-mole with variants, which we really cannot do, which is the reason why we do want to get boosters, but you can't give a different boost for every new variant, because we would have had maybe 25 separate boosts already. But the boost that you get generally covers a broad range of the variants. What are we really worried about? Something that I think is probably very unlikely, that we're going to get a variant that is so different than everything else we've been exposed to, that it's going to evade all the immunity that we have, and we're going to start from scratch like it was in January of 2020. You never say never when you're dealing with pandemics, but I really don't think that that's going to happen. I think we're going to continue to get different variants that'll evade immunity a little bit, but not a lot. Okay, including in lesson 1, asymptomatic and pre-symptomatic transmission is common. What does that mean? That means it's totally different than any other virus of the respiratory tract that we've experienced. With influenza, which is the most common respiratory-borne disease, 95 to 98% of the time, you get infected from someone who's sneezing or coughing or symptomatic. That tells you that if you stay away from sick people, you're pretty safe. Unfortunately, not so with COVID, because 50 to 60% of the transmissions with COVID come from someone who has no symptoms at all, which makes wearing of a mask very confusing in the beginning. Remember, we said you don't really need to wear a mask, and then when we realized that it was asymptomatically transmitted, we needed to wear a mask. Next, aerosol transmission predominates. What does that mean? There's droplets and there's aerosol. When you're dealing with droplets, if I sneeze or cough, droplets come out and they usually fall within 3 to 6 feet from you. With aerosol, when you breathe, the virus comes out and stays suspended in the air anywhere from minutes, sometimes even longer than just minutes. That is the reason why you hear so many stories of people that go into a room, go into a choir, go into a restaurant where no one appears to be ill. They go home and 5 people in the restaurant find out that they're infected, or 5 people at a wedding. That's what happens. And then finally, there's something we have not seen with other viral infections, and that's the post-acute sequela, often referred to as long COVID, which means signs and symptoms that are not completely explainable by readily apparent pathogenic processes, and they consist of everything from cognitive dysfunction or brain fog, as people say, dysgeusia, anosmia, fatigue, dyspnea, a variety of bizarre symptoms that people sometimes get accused of actually having a little problem mentally or emotionally, but it isn't. It's real symptoms. And the mechanisms of that range from persistent inflammation to viral persistence to immunological dysfunction. Bottom line, to save you the trouble of trying to scrutinize this slide, we don't really have any idea what causes long COVID, but there are some interesting new probing into potential disease mechanisms. It's serious because if you're talking about billions of people infected, about 9% of people in the United States, according to the CDC, are currently experiencing long COVID. Okay, that was a pretty complicated first lesson, but it's important. Second lesson, pretty simple. When you're dealing with a pandemic, what happens is you don't have a linear increase in cases. It percolates along, and then it explodes exponentially, which means that when you first detect that you're dealing with a pandemic, even though you only have a few cases, you've got to act like you're going to get a tsunami, because that's what happens with pandemics. Remember, we were looking at Italy, and Italy was getting smashed with the pandemic. We had 5 cases, and we said, well, maybe we'll be able to control it. Italy is no worse or better than we are. And if they couldn't control it, we were foolish in thinking that we could, which is the reason why for the next pandemic, we want to make sure that we have an aspiration that within 100 days of knowing you're dealing with a pandemic, that you can have diagnostic tests, therapeutics, and at least the beginning of a vaccine program that's ready to ultimately be distributed. That's aspirational, but that's what we need to aim for. Lesson 3, global information sharing and collaborations are essential. That is absolutely critical, because early on in the outbreak, we were getting mixed messages from China. The first call I got said, well, it's spreading from an animal to a human, and it probably doesn't spread very efficiently. A week later, you know, it's spreading actually pretty efficiently. 2 weeks later, holy mackerel, it's really spreading efficiently. And then we get an aerial photograph of China, which is building 1,000-bed hospitals overnight. Yes, that's spreading very rapidly. So we have to essentially get that information, which from some countries like Israel, the UK, and South Africa, we were getting information in real time, and it was extremely helpful. Lesson 4, leverage existing infrastructure that you have. About 40 years ago, I built a clinical trial infrastructure as director of NIAID, both domestically and globally, to test drugs, vaccines, and prevention modalities on a global scale. When COVID came, we needed a global network to test the vaccines in 30,000 people per vaccine. And we had 3 or 4 vaccines we were testing. So what did we do? We converted our AIDS clinical trial group and renamed it the COVID-19 Prevention Network. And each of those red circles are clinical trial centers that were utilized first for HIV, but now for COVID. And the success of that, I'm going to get to in a moment, was striking. Lesson number 5, prior scientific advances enable rapid countermeasure development. So the speed and efficiency with which we developed vaccines, and I'm going to show you the time frame in a moment, was totally dependent on literally 10 to 20 to 25 years of investment in basic and clinical research. And I'm going to dissect that out for you right now. When you look at vaccine development, it's two separate components: the vaccine platform and the vaccine immunogen. The platform is what kind of vaccine? Is it killed? Is it live attenuated? Is it a recombinant one? Is it a virus particle? Is it an mRNA one? The vaccine immunogen is what is the conformation of the protein that you're going to stick on to that platform and use as the vaccine. So let's take each of these separately, and I'll show you the point I'm trying to make about the investment in basic and clinical research. First, the COVID vaccine platform. We're all familiar with the extraordinary success of the messenger RNA or mRNA technology. The first paper that allowed that was actually 18 years ago in 2005, when two investigators, Katie Carrico and Drew Weissman, showed if you modify the RNA molecule in a way that prevents it from inflammatory responses, you can get an incredible platform for a vaccine. The next story is near and dear to my heart because it involves my own colleagues in my former position at NIAID. And that was the development of the COVID vaccine immunogen, which actually got its origin 20 to 30 years earlier in an attempt to make an HIV vaccine. So some of you may know, probably not a lot of you, that the Vaccine Research Center we established about 23 years ago. And I developed it with the help of President Clinton, who was very generous in making it happen, to bring together a group of investigators of multiple disciplines: vaccinology, immunology, microbiology, epidemiology, clinical trials, to develop at first a vaccine for HIV. And one of their key approaches was to get the structure-based design of the envelope of the virus to see if it was optimally inducing an immune response. So a classic paper was published in the journal Nature. On the right-hand side, all that squiggly, all that is the right and correct molecular conformation that was stabilized by creating mutations to allow it to be in a fixed form to be the perfect immunogen. We didn't get an HIV vaccine, but some investigators were very interested in a respiratory syncytial virus vaccine. And what they did is they used the same technology to stabilize the HIV envelope, to stabilize the correct immunogen for a respiratory syncytial virus. And that's an example of real collaboration between scientists. Because if I go back a few slides, the circle on the lower left, that red circle, is Peter Kwong, who's a molecular biologist, structural biologist, that is devoted to HIV and could care less about RSV. On the upper tall guy with the sunglasses is Barney Graham, who is in love with trying to get an RSV vaccine, who cares not so much about an HIV vaccine. They got together, and what you got was a successful RSV vaccine, which now, for those of you who are 60 years of age or older, you have an RSV vaccine available for you to protect you against a very important infection. But it didn't stop there. What happened when MERS came along, you know, that Middle East respiratory syndrome, we decided to make a couple of mutations to get the spike protein of MERS to be a good immunogen. So we, and when I say we, I mean my team at the Vaccine Research Center, they knew exactly what mutations to induce in this product to make it stable to be an optimal immunogen. And when SARS-CoV-2 came along, bingo, they made those mutations, And they did something completely unprecedented. Barney Graham told me in my conference room on the NIH campus, Tony, as soon as we get the genetic sequence of this virus, I'll start making a vaccine in 5 days, which is, crazy according to anybody's determination. It usually takes years. So I said, fine. On January 10th, the sequence came out, and Barney came through with this promise. And so the 6 or so vaccines that are made, look at the far right of the slide, that blue arrow that says S2P, that's the mutations in 2 prolines, which are amino acids that were responsible for making that immunogen that was perfectly stabilized. So what has that got to do with anything? What it's got to do with the fact that if you compare the time that you got the sequence with the time we put a vaccine in people's arms in November of 2000, this is what you see. Just like Barney promised, 5 days after the sequence, we had a vaccine going. 65 days later, we were in a phase 1 trial. 138 days later, we were in a phase 2 trial. 198 days later, we were in a phase 3 trial. And less than a year, 311 days later, the interim analysis said we have a vaccine that's safe and that's 94 to 95% effective, which is beyond unprecedented in vaccinology. Let me show you what I mean. This slide goes from the time you recognized what the pathogen is to the time you develop the vaccine. Well, in typhoid, it only took 105 years. With polio, 47 years. With pertussis, 42 years. Go all the way down and take a look at COVID-19. 11 months, which really saved, by that period of time, literally millions of lives. Because if you do any study, the Commonwealth Fund showed that just between December 2020 and November 2022, in the United States, more than 3 million lives were saved, more than 18 million hospitalizations, and $1 trillion in healthcare costs. We were not alone. In Europe, they did a similar study, and they found that in multiple European countries, 1.4 million lives were saved, and 67% were saved during the Omicron period, that later time I showed you. Not surprisingly, Science magazine deemed this the breakthrough of the year for 2020. Extremely unusual for Science magazine to deem a clinical trial the science breakthrough of the year. It's usually somebody cloning a gene or something like that. So Time magazine recognized that too, and they had a cover showing both Barney Graham and Kizzy Corbett together with Drew Weissman and Katie Carrico. And in fact, in their wisdom, occasionally, the Nobel Committee actually gave the Nobel Prize to Katie Carrico and to Drew Weissman. Well, Drew always says when he talks that he spent 6 years in my laboratory at the NIH, and the lesson I learned from taking care of and nurturing a brilliant person is put them in the right direction, give them psychotherapy when they're depressed, and get out of their way. And then they do something great. So Drew happened to win the Nobel Prize. Okay. Lesson number 6, priority pathogen and prototype. Priority pathogen means you a priori pick out a group of pathogens that you think are high enough risk to cause a pandemic, and you immediately start making interventions and countermeasures for it. This is a group that the WHO R&D blueprint showed. Lassa fever, Nipah, good choices. But probably a more calculated approach would be the prototype pathogen approach, which means that you pick out a particular family of viruses and you build on prior experiences. What do we mean? Well, we wrote about that, myself and my colleagues, but the credit really belongs to Barney Graham, who came up with that idea and presented it to me several years ago. What it means, if you look all the families of viruses, there are about 100 of them that can infect humans. About 30 of them can commonly do it, and about 7 or 8 of them are at a high risk of eventually causing a pandemic. And what you do is you take each of those families and you do commonalities. You study basic virology, assays for clinical settings, animal models, antigenic targets, optimum platforms, and a whole variety of things, so that if and when you get an outbreak in one of those families, you've already hit the ground running. Going back, look at the one on the upper left, the coronaviruses. We already had experience, some with the common cold, those 4 that I showed you, some with SARS, some with MERS. So when it was ready to go with SARS-CoV-2, we actually knocked it out of the park, as you've seen from that vaccine. Lesson 7, increase attention to the animal-human interface. Why? 75% of all the new emerging pathogens are zoonotic, which means their reservoir is really in an animal, and they jump species and adapt themselves to the human. We have ample history of that. HIV from a chimp to a human, Nipah from a bat, SARS from a civet cat, Ebola from a bat to a non-human primate. We've written extensively about that. The most recent one was a few years ago when David Morens and I wrote an opinion piece in Cell in which we said, and most scientists agree with us, that when the human species perturbs the balance between the natural environment and the human species, you can increasingly provoke new disease emergences. Now, we know how SARS emerged. We know how MERS emerged. We're highly suspicious, though we don't know for sure, that the same thing occurred with SARS-CoV-2. And a group of evolutionary virologists from all over the world, Australia, Canada, UK, United States, got together and did geospatial studies, virological studies, and epidemiology studies, and strongly suggest, haven't proven, but strongly suggest that the virus emerged from a wet market in Wuhan where there were animals that should not have been sold in the wet market because of not being sure what types of viruses they harbor. Now, the approach then to reduce the risk of pathogen spillover, it's simple. Expand surveillance of wildlife. It's not that difficult. It's called One Health, namely the interface between animals and human. Stop clearing and degrading tropical and subtropical forests. Improve the health and economic stability of communities that live in hotspots for emerging infections. Enhance biosecurity in animal husbandry. And importantly, I put it last, but it's the most important, shut down or strictly regulate wildlife markets and trade, because we have ample precedent for viruses jumping from an animal to the human under those circumstances. Lesson 8, this goes well beyond COVID. Long-standing systemic health and social inequities drive pandemic disparities. What do we mean by that? When you look at disparities with discrimination, limited health care access, occupation, people who are lower socioeconomic level, minorities, African Americans and Hispanics among them, disproportionately work in essential jobs that put them right in the middle of a risk of getting infected. Educational, income, and wealth gaps, and housing. Some people live in crowded, multi-generational homes. It's hard to do prevention strategies. Look at this disparity in vaccines. When you look at COVID vaccines administered per 100 people by income, look at the difference between high income in purple, upper middle in red, lower in green, and low income in blue. That is a profound disparity in access to a life-saving intervention. Now, the next is misinformation is the enemy of pandemic control. No doubt, it's really, I think, one of the most important issues we're facing. It goes well beyond COVID. 78% of the public believes or is unsure about at least one false statement, and nearly a third believe at least 4 of 8 false statements tested. I could give you 25 slides of that, but I'm not going to bore you with it. Here's some of them, just in the last 6 months, that were fact-checked by Political Fact. That there have been 17 million deaths associated with COVID vaccine. So in other words, COVID vaccine causes more deaths than COVID, okay? Iceland has banned COVID vaccines among soaring sudden deaths. No, not true. You're in danger because the American Red Cross doesn't label blood donations from donors that were vaccinated against COVID. Well, you don't really need to. Bill Gates and I, we're good friends, Bill and I, you know, we both put chips into vaccines to follow people. It magnetizes you, so stay away from me, you'll get clipped to a wall. And the CDC says that new COVID variants is more contagious among vaccinated than unvaccinated people. Completely crazy. Well, it's kind of ludicrous, but it's tragic, because the consequences of misinformation, at least 232,000 deaths has been estimated to have been, could have been prevented among unvaccinated adults during a 15-month period between May of 2021 and September of 2022, had they been vaccinated with at least a primary series. Multiple studies have shown that. 200,000 people died because they refused to get vaccinated. Truly a public health tragedy. Finally, lesson 10. It ain't over till it's over, as my good friend Yogi Berra of my childhood said a long time ago. What do we mean by that? What's going to happen with COVID-19? What's the end game for 2023, 2024, and beyond? When you look at pandemics, you look at it in multiple different phases. First of all, you ask a question. We're out of the pandemic phase because it's sort of low level now, so you ask a question. Are we going to eradicate COVID so that there's no more COVID? The answer is a resounding no. And the reason is that we only eradicated one pathogen in human history, and that is smallpox. Why? Because smallpox is phenotypically stable. It doesn't change. The smallpox that killed the pharaohs is the same smallpox that we eradicated in 1980. Number two, when you get infected or vaccinated with smallpox, your immunity lasts minimally decades, maximally for a lifetime. So we're not going to eradicate it. Next question, are we going to eliminate it so that there's no more COVID in the United States, but there's maybe COVID in other countries? The answer, extremely unlikely. Why? Because when you talk about elimination, 2 examples of elimination, we've eliminated polio in the United States, and we've eliminated measles. Why? Same thing as smallpox. Measles and polio are phenotypically stable viruses. So I'm old enough that I didn't get vaccinated with measles, but I got infected with measles as a child. So right now, the immunity associated with infection and vaccine lasts minimally for decades and optimally for a lifetime. Next thing is that the measles that I got infected with is the same measles that we're getting infected with now in low and middle income countries. So what about SARS-CoV-2? We're in trouble. One, as I've shown you amply on prior slides, there are multiple variants sequentially, so you're not dealing with the same virus. And number two, although we don't like it, it's true that the durability of protection against either being vaccinated or infected, the durability of that protection is measured in months to a year or more, which is the reason why we tell people they need to get a booster shot intermittently. So what are you left with? Controlling COVID, which is where we are now. So what do we mean by controlling? Well, some people say that's return to normalcy, it's going to endemicity. How do you do that? You do that by common sense respiratory hygiene. You do that by the availability of antivirals. But importantly, you do that by making booster shots available. Well, making them available and people taking them are two separate things. We have an excellent new booster shot that was put out about 7 or 8 months ago, the XBB1, that works beautifully against the current strain. Yet, when you look at the percentage of residents who have received an updated booster, these are the different age groups. You know what the mean is, the average? Less than 20% of the US population has gotten a booster shot. So let's close up with beyond COVID-19. Where are we going with these emerging infections? Well, about 3 weeks before I left the NIH in the end of December of 2022, I wrote a perspective in the New England Journal of Medicine, and I entitled it, "It ain't over till it's over, but it's never over. Emerging and re-emerging infectious diseases." New England Journal says I was an inherent depressive, but I wasn't. I was only fooling. But if you look historically, turn the clock back centuries, emerging outbreaks have been with us before recorded history. The plague of Athens in 400 BC, we don't even know what that was, but it killed a lot of people in Greece. In the 14th century, the bubonic black plague, we know now that that was Yersinia pestis, a bacteria, which killed about 50 million people at a time when the population of the earth was like 1/5 of what it is now. And you go all the way down to 1918, the pandemic of influenza, which killed 50 to 100 million people. So they've been with us forever. I became director of NIAID in 1984. The first time I testified before Congress, I had an artist drew it, a map of the country. It was 1984, and I put on the map HIV as an emerging infection. And I used that map for the more than 250 times that I've testified before Congress and said that each year we get 1 or 2 or more new emerging infections. The last time I testified was in April of 2022, and this is what the map looked like. These are all emerging infections, some of them trivial one-offs, but others of them turned out to be consequential. And so, when you look at selective emerging infectious diseases, merely from the period of 1981 through 2023, these are lists that should be familiar to you. We all know HIV in 1981. Lyme disease was new, at least newly recognized. Hepatitis C, bird flu, West Nile in 1999, MERS, SARS, chikungunya, Zika, Ebola, Mpox, and now COVID. So what does that tell us? It certainly tells me. And I wrote about it years ago in a paper with my colleagues in Lancet. And what I said is that emerging infectious diseases are a perpetual challenge. I've showed you that. It goes back to before recorded history. The only way to be prepared for the perpetual challenge is by being perpetually prepared. And for me, that is the final and most compelling lesson that we've learned from COVID. Thank you.
Please have a seat. I think you're here. Well, good evening. I'm Maria Conchan. I'm the Dean of the McCourt School of Public Policy, and it's been an honor and a privilege to have Dr. Fauci join us on the McCourt faculty and the School of Medicine faculty. And it's wonderful. I really appreciate your comments, and I want to use this opportunity. And it's been a long time since I've sat through what felt like a biology lecture. I gotta say, I'm not sure I followed all of it, so I look forward to following up with you on some of the pieces. But I want to spend just a little bit of time now sharing some of the questions that we've gotten, because people had many, many questions, and I want to just note that Dr. Fauci is a very generous participant in our community, and I know that you look forward to interacting with our students and our community going forward.
I do.
Yeah. So I'm going to start with just a couple of questions that we received in advance, and then I want to call your attention to the microphone that's there and say that we'll have time to take a few questions from the audience as well. So the first question I have is from Parth, a freshman in the School of Health, who asks, what was the pivotal moment in your life that made you realize your medical career should include public policy?
No, that's a good question. And it really dates back to the very first years from 1981 on with HIV. Of course, when HIV came, it was really historically in our generation the first brand new public health crisis that was global in nature. And I had been at the NIH at the time, after I finished my chief residency in medicine, which was in 1972. From 1972 to 1981, I had been involved in studying the interface between infectious diseases and immunology. When HIV came along, I turned around completely the direction of my research and focused completely on, at the time, this interesting new disease, almost exclusively in young gay men, that was not only in the United States, but all of my colleagues around the world were saying, we have the same sort of cases. It was at that point that I realized that if I really wanted to pursue this, which I did, and I have been doing that for the last 43 years, I'd have to get involved in global health and in public health. I couldn't be provincial in just a very restricted disease. It had to be global, and that essentially was the inciting event that allowed me to make the decision when the job came up to become the director of NIAID, which gave me the opportunity to study not only HIV, but all of the diseases of global health impact: malaria, TB, neglected tropical diseases.
And did you realize that you were going to become a policymaker, that there was going to be a policy and political piece to it?
No, not at all. And in fact, that just, and I tell that to students all the time, one of the exciting things about an evolution of one's career is that very often you can plot the direction of where you want to go, but almost invariably, and to a greater or lesser degree with different people, events get thrown in front of you that are either opportunities or stumbling blocks. And it's nice to make them opportunities. And the idea of getting involved in policy became an absolutely essential component of the global health issue. I had to get involved in policy making. But I have to say, Maria, that don't confuse policy with politics, okay? Getting involved in policy doesn't mean you need to get involved in the politics, which sometimes spills over into public health, almost invariably for negative consequences.
Yeah. Well, I'm glad that you remain optimistic about keeping those two things separate.
Yeah.
I think it's many of us try to maintain that separation, some with more success than others. So I have a second question from Matthew, who's a freshman in the College of Arts and Sciences. Why do you believe there is such rampant skepticism towards health officials during times of health crisis?
Yeah, I mean, I could even modify that question. Why is there skepticism towards health officials in any situation, and it gets exacerbated in health crises? Because health crises amplify a lot of things that go on in society, for sure. But one of the things that, to me, is really troubling, and it relates to that question, is that we are living in an arena or an era of what I call the normalization of untruths. And the misinformation and disinformation that spreads around is stunning. I mean, to the point where if you normalize it and accept it, then truth has no value. And when truth has no value, science falls apart, because science is a process for getting to evidence, data, and truth. And if you take that away, then skepticism abounds. Who are you going to believe? You're going to believe a health official? No, because they said that this was going to happen and that happened. So, you know, when I hate to be giving lessons to audiences, but spare me here, is that if there's anything that you can really do to help your country and society, is push back on this normalization of untruth. Don't accept it as, well, that's the way things are. Because once we accept that that's the way things are, the democracy is going to fall apart. It really will. And I'm not being hyperbolic about it. That's what's going to happen. So it goes well beyond skepticism of public health. It's in all the society.
Yeah. I would agree with you, and I think that's a particularly important sentiment at this university, in this city, at this moment. So again, I'm going to invite people to line up behind that microphone if anybody has a question. Otherwise, I'm going to keep going. So I have a question from Sean, who's a sophomore in the College of Arts and Sciences. What considerations were taken with regards to working with state governments with significantly different structures and outlooks on pandemic response? What lessons about federal and state cooperation did you learn?
Yeah, you know, that's another great question. Good question. So
we have smart students
yeah,
here
pretty
at
smart.
Georgetown.
I noticed they're all from arts and sciences. Where's the business guys?
No.
Sorry. So one of the real weaknesses of our response that we didn't see in other countries was the disconnect between the federal government's response and the local, state, and city responses. Because the way the setup is in the United States is that the city governments and the state governments are really somewhat independent from federal control. So they don't necessarily have to give the CDC the data that the CDC needs.
Absolutely.
They give it to them if they want to give it to them. And you can't force them to do it. So when we were dealing with trying to get real-time data as to what was going on, believe it or not, that we had to go to the UK, to South Africa, and to Israel to find out in real time what was going on with the trends of the new variants, which was really kind of bizarre. We have a country of 330 million people, the richest country in the world, and we can't get real-time information from the states and the cities.
I feel like that's a little bit of an infomercial for McCourt's Data Science and Public Policy program, but I'll put that aside. I'm going to ask for the first question from the floor. Please say who you are and what your school is.
Hello, Dr. Fauci. Thank you for visiting us. My name is Andrew, and I'm a student in the McCourt School of Public Policy. You've spoken to us about science for public policy, but I want to ask you about our policy for science, especially on research. Since Vannevar Bush, the consensus has been, as you noted, you have really smart investigators, you give them money, and you get out of the way. And the idea is that investigator interest and personal passion should really drive, especially basic research pursuit. My lay understanding is if we know the 8 sources of most likely pandemics, well, we should just restrict our funding to make all our brain power available, work on that. As you noted, there's really, really smart colleagues who, they don't care about HIV because it's not their interest. Is it feasible as a public policymaker to think about directing basic research more, even advanced research more? Yeah. Would it be feasible? Would it work to change this consensus to try to bend the arc of what research looks at and why, or no?
Thank you for your question.
Another great question. The answer is you have to do both. And what there is, at least, my institute was the second largest institute at the NIH, but all of the institutes have the same mandate, and that is to have a balance between programmatic initiatives and fundamental, undifferentiated, unsolicited research, where you just ask somebody to come up with an idea. Because the basics that I showed in those 2 slides of what Katie Carrico and Drew Weissman did and what the HIV people did, nobody told them what to do. They were just doing things because they thought they were interested. That has to be balanced against what we call programmatic direction, where you don't tell somebody what experiment to do, but you say, when we had the emergence of HIV, we put a lot of money into HIV research and said, we need to look at pathogenesis, we need to look at the development of a vaccine and the development of drugs. That's the degree to which you push people, but you don't tell them the experiments to do. So the answer to your question is you have to have a balance. You can't let people just free float, do whatever they want with no programmatic direction, but you can't have only programmatic direction because you'll inadvertently suppress some really important spontaneous ideas.
Thank you.
Thanks for your question. Next.
Hi, Dr. Fauci. My name's Dua, and I am a junior in the college majoring in biology of global health. First, I just wanted to thank you so much for coming here and being able to bless us with your presence. My whole family is a great fan, and you touch the lives of so many people in low-income communities and middle-class communities that I'm part of. So I just wanted to thank you for that first. And my question is along similar lines because you mentioned how low-income communities have the lowest vaccination rates, and low-income communities also have the greatest hospitalization rates, such as what we see in wards 8 and 9 south of the Anacostia River in DC. So I was wondering if you have thought of any policies that we could start maybe locally in DC, and if there are any specific tactile legislation that Georgetown students can advocate for with local congressmen in order to start addressing some of those systemic barriers locally to basically barriers to hospitals, because they're all clustered in Northeast DC, as you know, and how we as students can be better advocates for those.
You just outlined most of the problems in society. I'm not being facetious. All of your points. First of all, I can tell you that you have to be realistic. There's not going to be a legislative fix for the ailings in society. Those are deep-seated social inequities that are going to take decades to overcome. We should not be put aback by the fact that it will take decades. It took decades for the social inequities and the social determinants of health to take effect. It's going to take decades around. But some of the things you can do obviously relate to reforming the healthcare system to have equal access. You can have equal access in our own country, in our own city of Washington, D.C., if you try hard enough, but you've got to put the resources into that. You've got to understand, making vaccines affordable and not say they're free for now, but then the way you're going to get them is when you have insurance, and then you have 20% of the people don't have insurance. You can't do that because that's just begging to enhance the inequity. So I think it's a long game of looking at decades, and then it's the short things about accessibility right at the community level.
Thank you.
Thank you so much.
So we're going to take 2 more questions because I'm getting signals from the timekeepers.
Good evening, Dr. Fauci. My name is Michael Subovaro. I'm a first-year medical student at the Georgetown School of Medicine. Thank you for giving us your time. My question is, given the undeniable link between climate change and the emergence of infectious diseases, how should future pandemic preparedness plan incorporate climate change projections to better predict and mitigate the spread of diseases, particularly in regions that are disproportionately affected by environmental changes? And my second follow-up is, as a medical student, what specific areas of training do you recommend we focus on as the next generation of physicians to be better prepared?
Yeah, okay, the first question is easier to answer, but well, I'll answer both of them. The idea of climate change is that you can't take emerging infections and say, I'm going to do something about climate change that is going to negate the negative effect of climate change on emerging infections. You've got to be part of the movement, the broad global movement of taking a look at climate change and its effects. I could give you so many examples of, we used to think maybe this was the case years ago, but now it's very clear that climate change, warming, et cetera, have absolute effect on the emergence of infectious disease, from the range of mosquitoes and other vectors like ticks, to rising of water levels leading to floods, which lead to the emergence of infectious diseases. So there's no doubt that it's there. But what we can do about it, I think, is to be part of the movement. And the medical community, yourself as a medical student, I mean, every school in Georgetown, you know, from public policy to business to clothing. By the way, don't get it wrong, I love the guys from business school. But every aspect, I really do. They all up there in the gym with me when I work out at Yates. So that's the answer to your first question. The second question is, you know, what can you do at your stage for doing that? I just think is have a degree of sensitivity among yourself and your colleagues about the importance of local public health. Not everybody in your medical school class is going to want to be in public health. But for those who do, and maybe that's you, it's really an exciting field. Just like every other subgroup is an exciting field. But if you have a passion for it, it really is important because of the extent to which you can influence large numbers of people. So I can't give you the specific answer to your question, but I can only encourage you that if you have an interest in that, it's really worth pursuing.
Thank you. Also, on behalf of the medical school, we're really excited to see you on our side of campus whenever you have some time. Thank you.
Okay, last question.
Hi, Dr. Fauci. My name's Catherine, and I'm a freshman in the SFS. And I wanted to ask you a little bit about the backlash that a lot of the politicians and the government were facing early on in the pandemic, especially a lot of the politicians who wanted to kind of act early and act more aggressively were getting a lot of public backlash. Do you have any fear that the government's need to be seen as credible or to be liked by the public will negatively affect the next pandemic response? And if so, how do you combat that as a scientist?
Yeah, I mean, I think that politicians in government right now, and it's really sorry to see that, have really had, in some respects, a real negative impact on our response to the pandemic. And I don't know how we're going to change that. They've politicized a very important event in our existence, in our history. The worst pandemic in well over 100 years has been egregiously politicized. And as I've often said, the worst thing to have just a pandemic is to have a pandemic in an election year with a divided country. And that's exactly what we had. So I don't know what the solution is, but I would hope that the better angels in people will realize that when you have such government level politicization, it leads to unnecessary deaths and hospitalizations. That's not hyperbole. If you look at the country on a map, red states, blue states, the proactive push against vaccines in red states versus blue states leads to a highly significant disparity in more deaths of unvaccinated people among Republicans than among Democrats. Now, I'm not a Republican, I'm not a Democrat, so I don't have, any emotional response to either, but it just seems as a physician and a public health person, it's so tragic that a person will statistically have a greater chance of dying in a pandemic because of what political party they belong to. But that's exactly what's happened in the United States. So I didn't answer your question of how to counter it, except to say how pained I am to see it happen.
Thank you so much.
And thank you for your questions. I'd like to, it's a wonderful thing that you will be with us and in our community for quite some time, so we'll have opportunities for more conversations. I want to thank everybody who's here. I'd like you to join me in thanking Dr. Fauci. I would ask that you stay seated until I've had an opportunity to escort Dr. Fauci out of Gaston Hall. Thank you.
Thank you.